Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on CO2 sequestration modeling. And today we will use tNavigator software to model the CO2 injection, CO2 sequestration. Okay, in previous part, we have discussed about this one. So if I open files and then to show you the master data or the data set, we have talked about all the keywords and the data here. If I'm not mistaken, down to grid ops and CO2 sol, which is a very important keyword for our operation. This is to enable CO2 dissolution in the brine. And we reach unif out, which is to save calculation results. Okay. And now I'm going to show you the grid, the properties, and the regioning, solution, and then schedule, hopefully. Okay, so for the grid section, or maybe, okay, so if we open grid here, so as you can see, we have several grids like ECNUM, mode PV, NTG, PermX, PermY, PermZ, and Poro. Actually, there's no special grids in this, in this model. So if I show you, this is for block X, along Y, and along Z. This is for the depth, tops, net to gross. Okay. And then this is grid for the porosity. So basically the distribution of all these initial properties like porosity, permeability in X, Y, and Z are taken from this data here. Okay. All right. So that's about it. And this is standard pore volume. And we have also aquifer support. In this model, we will use Carter Tracy. Okay. And the calculated properties, like if you open, this is the distribution for pressure, saturation of oil. So no oil here in our model. Water, everything is water. So basically it's an aquifer model. No gas. Okay. And then, all right, this is 1 divided by formation volume factor, nothing so special. Mass density of water, no for oil, no for gas. Molar density of water. Okay. So basically this is the density of water. Okay. And later if you inject CO2 and the CO2 will be dissolved into the water, the mass density will be changed. And then this is the data for relative permeability of water, oil 0, gas 0, everything will be water. And we are currently using, compositional modeling. If I'm not mistaken, we use compositional modeling. So we can trace the component here, calculated. We have component water and component CO2. Of course, we will use compositional modeling because we want to track also each of the component, in this case, especially CO2. Okay, and then regioning, we have PVT region, only one. Saturation regions, we have two regions at the upper section and the bottom section, but it's actually not the main issue here. Raw compaction, only one. Equation of state region, only one. Equilibration region, only one, right? The regionization is not the main issue here. Endpoint scaling, okay. And then FIPNUM, only one. Active grid blocks, only one. Okay, and you can skip the interblocks flow and then vector fields, and then user cut, still empty here, will not be used maybe. User map also. Okay, and then, so that's it for the grid properties. And then graphs later. Water flood, no. Fluid properties, this is important. Okay, first for the relative permeability, as you can see, we have two regions. All right, which one? This one, saturation region. So for region 1, we will use this package of relative permeability. And for the region 2, the bottom zone, we will use this one, which actually the same. Okay, so basically no issue, right? Same, both for the water oil and gas oil. And this is the numerical values. And you can input this data if you go to the props and then relative permeability here. So basically for relative permeability water oil, we are going to use Cori function. And if we go here, this one, so you can see the numerical values. I'm going to show you the file. So here 1.2, 0.2, I mean, this one 0.2. And then you can follow the number 1, 0.2, 0.2, 1, 1, right? And then 4, 4, and then -1. So basically for SWS, SWL, minimal water saturation 0.2, you input here, and so on and so forth. This is for the first region, and this is for the second region. Okay, you can see region number 1 and 2, which actually if you check the values here, the same. So basically it's just one zone. And then here, RP, relative permeability gas oil, again, we will use Cori function. Thus the keyword Corigo and Coriwo, and these are the numerical values. See, 0, 0.8, you can see there, 0.05, and so on and so forth. Okay, perfecto. And then rock is, we can take this value from props and here, props. Okay, so the rock compressibility, the keyword is rock, and the value is 100 for pressure and 9 to the power of -5 for the rock compressibility. And then this is very important, the solubility. Okay, the solubility. Because we are dealing with CO2 dissolution, you need to provide the solubility, right? The solubility of CO2 into the brine. And this is the table. We have provided the model with first the keyword and the values. You need to use, maybe your measurement from laboratory, or maybe you can just take from literature and then you input it here. Just make sure you are in the range of working pressure. Like in this case, we have input for 1 up to 1013 because we are playing with that pressure during the simulation. Okay, so what else? This ncoms, because we are only dealing with one component, one compositional component to be exact, which is CO2. And then here we want to take the PVT data from this. We will check this file again later. .inc. This is keyword for rock compressibility, and this is for the relative permeability, the one that we just looked previously, checked solubly. Okay, that's it for the props. Okay, and then we will go back and check for the PVT. The first one is here, component properties. And maybe we can check props and then PVT here. Okay, so we have one component. The keyword is ncom1, and the component name is CO2. That's why we define with this keyword cnames CO2. And then for this, the table components properties, we have critical temperature. The keyword is tcrit here, 304.19, and then critical pressure in bars absolute, pcrit, 73.82, and then critical volume, we have this vcrit, and then critical Z factor. We are not talking about the basic of all of these properties, right? So we assume that you understand each of these properties. In this case, Z factor or deviation factor, we will use this value and this keyword. Okay, and then Z crit Fis, we also provide that. ZI molecular weight, molecular weight, 44.01 for CO2. And then eccentric factor, ACF 0.228. And later, boiling temperature, critical volume 0.094. Okay, it's good. Eccentric factor, good. Composition here, this one. Okay, good. And then, okay, that's good. That's for the components properties. We have checked the numerical values and as well as the keywords. And then let's check the component surface properties. Okay, actually the same with component properties and component surface properties. Now components interaction, because we are dealing only with one component, so there is no interaction between CO2 and other component. We don't have other component. So that's why our BIC is blank here. Binary interaction coefficient between components, blank. If you have more than one component, then there will be interaction, binary interaction between one component and another component. So it's binary relationship. Like for example, CO2 and CH4, CO2 and then nitrogen, CH4 and then nitrogen, and so on and so forth. If you have more than one component. Okay, so we only deal with one component, so there is no interaction, there is no binary interaction. So that's why we use like this. Okay, and then we have for this same relative permeability, basically equilibrium. Equilibrium, we will take that from solution. Wait a minute. Here, for equilibrium, we have two zones, two regions. This is for the depth, you can see there, and then pressure, and then this is for the gas water contact or water oil contact, and so on and so forth. This is for our aquifer Carter-Tracy, AQCT, and this is Equancon. This is connection, okay, connection between the aquifer and the model and the reservoir, or yeah. By the way, I have video about aquifer modeling, so maybe you can refer also to that. And this is basically for reporting or the resulting RPT map and so on and so forth. RPT graph, right? And then for the summary, I'm not going to describe or explain all of these keywords. You need to check the user guide or user manual to understand what, all these keywords mean. Okay. And then VFP table for injector. We have that in schedule. So if you have modeled or your injector And then you create basically the VFP, vertical flow profile, to connect between bottom hole pressure and wellhead pressure as a function of like GOR or gas water ratio, something like that. You can input it here. Okay, we have, injector 1, injector 2, 3, 4, 5, 7, 8, right? Blah, blah, blah. Hopefully later on I can talk about all of this, yeah, VFP specifically, but we will not deal with that in this video. Okay, so I think pretty much that's all. This is for the schedule. Okay, again, scheduling is basic. If you check schedule here, it's basic, and we are not talking about that. But maybe something special is here because we want to inject something. Then we will use this keyword well stray, all right? Stream name, mole fraction. So the stream name is inch gas and the mole fraction is 1, so 100% CO2. And then this is the first date. This is the keyword for well location. This is the keyword for well completion. This is for the input that the well will be on stream. And then this is we inch gas. Okay, we basically define the stream for each of the injector. And this is the operating condition for the injection, like the bottom hole pressure, something like that, open or shut, something like that. Okay, so that's it. Hopefully, if we have time and opportunities, we can deal with this in more detail. Okay, by the way, we connect the model with the VFP and the well trajectory using these keywords. Okay, that being said, let's go to the main course. Maybe saturation of gas, we can start here. So as usual, we just need to click, run. And then you can see we have 9 wells here. Okay, injector 1 to 9. And then you can see at initial time, at early time, saturation gas is 0. Now we inject CO2 in gaseous phase. Okay, because if you check our keyword files here, do we have rtemp? Wait a minute. Okay, reservoir temperature. We are going to find that maybe in, not here, but do we have that in grid? No, of course not. PVT, do we have something like temperature? Yeah. So now the reservoir temperature is at 35, all right, 35 degrees Celsius, the 35 centigrade. And with the pressure that we have here in bars absolute, the gas inside the aquifer will be in gaseous phase or supercritical phase, if you are familiar with that term. Okay. So CO2 will be in the gaseous state or supercritical state, because in this model, the supercritical state will be regarded as gaseous phase, gaseous state. Okay, so continue. All right. We can also check to saturation of oil. Still no oil, right? Because we are not injecting oil. We are injecting CO2. But CO2, the supercritical CO2, will be considered in the model as gaseous state. That's why we have saturation gas here. By the way, this is the default from the tNavigator. Of course, we can change the location of the injector. If you consider it to be too tight, the spacing, you can basically move this injector down there, and so on and so forth. Okay, so the injection or the operation, the simulation completed. Now we are going to make sure that we are now in supercritical state. So if we maximize and touch the grid, right click, we can click this one, click on this one, show in PVT designer to know where we are actually in the phase diagram. So click on that. Okay, so this is where we are. So now we have the PVT designer window. Let me squeeze it. Okay. So again, you can right click in this gaseous area, right? And then you can right click and yeah. So now we are located at this critical point. You can see here the yellow color critical point, and our location is, if we expand, is right there. So if this is the critical point and we are located up there, it means that we are in supercritical state. Below this point, we have really the true gaseous state. At that side, we will have liquid state, but at that side, we have supercritical state, to be exact. Okay, so we have, confirmed that when we inject the CO2 in the given reservoir temperature and pressure, we are injecting in supercritical state. We have the phase envelope for the CO2. Okay, and we are currently taking the point from this cell, X31, Y48, Z1. Of course, you can also check the condition at other grid, but that will be the same thing. We are injecting in supercritical condition. Okay, and then let's check the pressure. So it's like this. You can move around to see the pressure change, right? You can also observe the injection propagation based on the pressure there. Starting from this condition, move to the right, you can see the increased pressure, and then more and more the pressure is increased. The pressure propagation expanded or propagated, right? Okay, so, and then graphs, of course. We are not interested in oil rate. We don't have oil rate and water rate. We are interested in gas injection rate, and we can model that. And we are also interested in pressure, but we cannot plot it at the same plot. We can do that in graph template, but later we don't have, not in this video. So you can see we can plot the gas injection rate in million standard meter cube per day from the starting of injection to the last time step. So it's easy. And lastly, analytics. FIPNAM, we can also model the number of moles of CO2 in water and then trapped in gas by the residual trapping, and then mobile, free CO2. Okay, but we will not talk more than this. So I think we can close this video first, and later on we will open the new video where I will explain more about this result. And we can also model the CO2 injection in liquid phase. Okay, but I think we can call it a day. Thank you so much for watching. I hope this video is useful. I hope this video is important for all of us. See you again in the next CO2 sequestration modeling using tNavigator videos. Thank you.